So first we got to solve this little calculus riddle so we know what we're doing. The first calculus thing that we did will be the last calculus thing that we do. So what is the thing? Well, if you were listening, I kind of gave it away. It's limits. Limits. Okay, now if you were trying to think about like the first day of school, that wasn't technically a calculus concept. But really, when we started calculus, the first real calculus concept was limits. Okay, so as you're going to find out here, we have a kind of a new way to find a certain type of limit. Now, if you're like, oh my gosh, limits, I don't remember that. It was so long ago. Here's a quick limit review. Jot it down if you want to, read it. Again, I just want to make sure you realize what we're trying to find. Remember, it's an intended height. The other thing that maybe you're experiencing here, maybe you are experiencing a little bit of, I do remember that. If you do take calculus again, like in college, I hope you remember, I hope you experience that a lot. Well, what I've shown you this year is definitely your money's worth. Okay, this has not been a watered down version of calculus. So if you take calculus again in college, it'll be very similar, which can be a great thing. Okay, it can be a great way to get started after high school. Now, let's talk about some limits. I actually have it up here right now. The limit as x approaches 0 of x squared over 2x. Same thing, I'm not sure maybe what you're experiencing. Maybe you're like, don't call on me, I don't remember how to do that. But I bet with a little bit of just showing you some work here that can come back to you. First of all, you should always plug in. It's kind of like the substitution method, we technically call it. But if you plug in 0, it's not hard to do. If you plug in 0, you quickly realize that you get 0 over 0. Now, don't go tell somebody that your teacher told you that that's equal to 0. This teacher didn't tell you that. 0 over 0 is not equal to 0. In fact, I'd rather that you remember it's something called an indeterminate. An indeterminate, as it says, does not determine anything. It's a meaningless expression. Honestly, it's a roadblock, meaning that you need to turn around, you need to do something else. Now, the something else that we're going to do is new. The something else we're going to do is we're going to actually do a derivative. Now, we're going to do the derivative. Whoops. We're going to look at the graph. I forgot. Let's look at the graph so that we can just kind of see the limit. This would still be what you would have done 8 months ago or so. So, the graph of x squared over 2x, well, I happen to have it here. It looks like a straight line, but it does have a hole in it. And of course, the place that we're looking at happens to be at that hole, which is the intended y value. So we have this intended y value of 0, which, by the way, is the limit. Okay, now again, that would have been how you would have approached this problem, or at least one way that you would have approached it some months ago. Can I show you a new way to find the answer of 0, which, as I was getting at, it has something to do with derivatives. What we're going to actually do is the derivative of the numerator and denominator. We're going to do the derivative of the numerator and denominator. All right, now make sure you're thinking derivatives. That's when you bring the exponent down. Right, that's when you subtract from the exponent. Correct. Just a little bit on the side note here. Just a little side note. I didn't do the derivative of the fraction. I didn't? No, I didn't. Because if I did the derivative of the fraction, that would have required the quotient rule. Same thing. If you retake calculus, Make sure you don't tell your professor, my teacher said I could do the derivative of the numerator and denominator. No, you got to do a quotient rule. But if I'm doing a limit, now I am telling you something new. If I'm doing a limit, well, yes, I can do the derivative of the numerator and denominator. Okay, so it's like a different goal here. The goal is to find the limit. Now, I hope you feel like those 2's would cross out. So, geez, it looks like we just end up with x. You know, the limit of x. Oh, like substitute in 0? Sure, substitute in 0. It's easy. And of course, you get 0. Trying to get all the sound effects in the last presentation here. What did we just do here? Well, it's a new way to find a limit of an indeterminate. That's important. What we just did here is how you can find a limit of an indeterminate. And basically, you can do the derivative of the numerator and denominator. Let's show you another one. It's meant to be not so nice. Okay, you look at something like this, and you might not even want to try to do the limit the old-fashioned way. You'll get the limit of the square root of 1 plus x minus 1 all over x. Fun stuff. Now, seriously, if you graph this, which is one takeaway from some time ago, you could probably find just about any limit if you graph it. But we're trying not to do that, so we're going to think about doing something more like an algebra method. Listen, you have to plug in 0 first and see what's what. Are you kind of doing that mentally? If you plug in 0, you get the square root of 1 minus 1 over 0. Well, that's 0 over 0. Why is that so important today? Well, because you can only do this derivative thing if you end up with an indeterminate. So, hey, good news. We got an indeterminate. That means I can do the derivative of the numerator and denominator. Now be careful, the derivative of a square root, this has popped up a few times in the last few weeks. It's more of something from last semester, but the derivative of a square root involves a 1/2 exponent. 1/2 exponent, right? If you subtract from a 1/2 exponent, you get negative 1/2. Technically, you got to do the derivative of the inside. That's called the chain rule, but that equals 1. So there's your numerator, and then the derivative of the denominator. Who doesn't like doing that once in a while? Now, it's not a bad idea to clean up the negative exponent, and I know you're not supposed to have a square root in a denominator, but as long as you don't tell, I won't either, because all we really need to do is plug in 0. Remember, when you're finding a limit, many times, almost all the time, it finishes with a substitution, like plugging in 0. Well, look, if you plug in 0, it works. Okay, you get 1/2 over 1. And of course, 1/2 over 1 is 1/2. Now, it might kind of seem like I'm just making stuff up here, but it's actually a rule. And the rule is, if I have an indeterminate, I can actually do the derivative, and you'll start to notice that what the derivative does is it actually gets rid of the indeterminate. It's kind of like I derive it away. I make the exponents go away, so I get rid of the 0 over 0. And in the case of this problem, I get 1 over 2. It's called L'Hopital's rule. L'Hopital's rule. L'Hopital was a mathematician from the 1700s. It was right around the time of all the controversy, and many things were being discovered and figured out. And so he was kind of working on basically the limit, believe it or not, of an indeterminate. And he found out that essentially the limit of f over g is the derivative of f over the derivative of g. It's a really easy rule to write down or to just understand what it is. Again, it's the derivative of f divided by the derivative of g. Now, the thing that's flashing right there, that's pretty important. You'll realize why. You can't do this rule unless you have an indeterminate. I'll show you why that's so important, because it'll happen in every problem. This will kind of be the verbal rule. The verbal rule is that it's essentially the derivatives evaluated at a. If you're wondering why x became a, well, we plugged it in. We evaluated. Just a little sort of side note, if you do take calculus again, outside of these four cozy walls, don't be one of those students that's kind of like, oh, I know another way that we could do this. You want to kind of relearn calculus. So don't use L'Hopital's rule if professor's kind of, starting at the beginning. Use it as an opportunity to kind of learn calculus again. But if it's discussed or you get to this step, you can use L'Hopital's rule for an indeterminate. You can't use it for like every limit. It has to be an indeterminate. What's an indeterminate? It's these meaningless statements. Okay, so I didn't do an infinity over infinity, but we will, or a 0 over 0. Let's see if we can do a problem or two today, and we'll do a problem or two tomorrow. And then again, you actually have another assignment, but it's really just on a piece of paper to get you to practice a few of these. And usually the rule gets used when there's a tough limit, okay? A limit that you might not be able to honestly have. I know we didn't even go over a limit like this because kind of the old methods don't work. And if you're saying, what's the old methods? Well, we can talk about that a little bit, or again, you'll kind of learn them again if you retake calculus. Square root of 1 plus x, that looks fun, minus 1, minus x over 2, all over x squared. Crazy function, trying to find its intended value as x approaches 0. Now, this is important, okay? You really need to go through this exercise, that is to substitute in 0 and see what you get. I'm just going to kind of do it mentally, because if I substitute in 0, I get the square root of 1 minus 1. That's 0. And then if I substitute in 0, I get minus 0. And if I substitute in 0, okay, I get 0 over 0. That's actually kind of a green light that says L'Hopital's rule. Now you can use L'Hopital's rule. Okay, so we kind of have to be careful how we're using equal signs here. It's more realizing that the next line of math, it is going to be equal, but I now have done or will do the derivative. All right, so kind of purposely doing another square root, making sure that you guys are doing the 1/2 thing. I hope you're changing the square root to a 1/2 exponent. I hope you're subtracting. That's why we get negative 1/2. Make sure you multiply by the derivative of the inside, which would be 1. So we're good there. Now, the derivative of minus 1 just disappears, but how about the derivative of minus x over 2? Be able to think of this as, I don't know if we really need to make a big deal out of it, but think of it as 1/2 x. It's just 1/2 x, or really it's minus. So the derivative of 1/2 x is just going to be the coefficient. All right, but it's often seen as x over 2. although it's the same as 1/2 x. Do the derivative of the bottom. Ready? You're gonna see something new now. You've seen a couple problems. You're ready for the next thing. Substitute in 0. Either do it mentally or physically. Substitute in 0. Now you might want to get a calculator out, but just relax. 1 to any power. Kids, 1 to any power is still 1. Times 1/2, minus 1/2. I'm getting 0 over 0. Well, sort of the rule is, or the idea is, that you continue to use L'Hopital. You continue to use L'Hopital until you get rid of the indeterminate. So nothing wrong, but we have to do another derivative. And as you guys will see, we're really doing the derivative to try to get rid of the problem. We're trying to get rid of the problem. What's the problem? The problem is getting 0 in the top and bottom. Now, when you do the derivative of the negative exponent thing, it just gets more negative. Negative 1/4, 1 plus x to the negative 3/2. Things are disappearing. That next 1/2 disappears. Now we look at the denominator, the x disappears. Just a little hint that that's really, the problem has just gone away. Once x disappeared from the denominator, I don't have the possibility of having 0 over 0. But I better check what I do get. So substitute in 0. Same thing, 1 to any power. I don't care if it's negative 3/2, it's still 1. So I get 1 times negative 1/4 divided by more. I hope that you would simplify that to be your final 1/8, negative 1/8. So now you saw something else that you can use L'Hopital. Well, you can use it as much as you have to until you get rid of the problem. We'll show you one more. It's nice to have another one to look at today. Sine of x over x squared. Just kind of curious for those that you can remember or want to remember the first part of the year, there was a special function that was similar to this. It was the sine of x over x. Just kind of wondering, do you remember the sine of x over x? Okay, but that would have kind of been the old way to go through the problem. The new way here is to think about, honestly, plugging in 0. Now, if you plug in 0, you get that green light because you end up with 0 over 0. Somebody says, do I really have to do that? Well, what if I give you a limit, and I will, that doesn't come out to 0 over 0? Okay, well, then you just get the answer. If I can plug something in and I get some other answer, then that's actually even nicer. So what I'm getting at here is don't use L'Hopital unless you have an indeterminate. But since we have an indeterminate, it's derivative time. Okay, and the derivative of sine is cosine. Derivative of x squared, well, you know that. I don't take the calculator away from you. You're going to plug 0 in here. Again, I don't take the calculator away. It doesn't hurt to remember, though, that sine and cosine are just values on the unit circle. Now, if I plug in 0, that represents a rotation of 0. So if I rotate 0, I'm basically at this point. Now, that point has a x value of 1. It also has a y value of 0, but the x value is the cosine value. Okay, so if I plug in 0, I get 1. If I plug in 0, I get 0. Ooh. Wait, 1 over 0. Okay, well, that's not an indeterminate, so, don't use L'Hopital again. So if it's not an indeterminate, then what is it? What is 1 over 0? Back in limit land, it would have been an expression that we called an expression that you recognize. Recognize means that if you get 1 over 0, then you make a conclusion about the limit. I'll gently call it remember your limits. Okay, so remember your limits, because if you get 1 over 0, that actually means a certain answer. It means that the graph is intending to get close to this is always kind of a strange moment, because people are like, wait a minute, you can divide by 0? Well, is that really an answer? Like, is infinity really an answer? In other words, if your limit is trying to tell you that you're dividing by 0, what that really means is that the graph is just going on and on and on. So infinity really means that there's no limit. But we would still write infinity. While we're remembering our limits, maybe we should remember what happens if you get 0 over 1. Now, don't think too hard on this one, because even if you're sitting in another math class and you get 0 over 1, I hope you would say 0. We haven't seen this today, but we'll put it in the chart so you have it. Remember, if you're dividing by infinity, I guess, if you want to think of it that way, but if it's 1 over infinity, that really means that the graph is getting closer to 0. If I divide something up an infinite amount of times, the graph's getting closer to 0. We actually would call that a horizontal asymptote. And then if it's infinity over 1, that means infinity. Remember, these things up here, they're like expressions to recognize. Okay, they're not necessarily like all of them equal to numbers. The 2 in the middle are equal to numbers, but this one is really just equal to infinity, which means that there's no limit. Or as the one mean girl said, the limit does not exist. Okay, just kind of giving you a little taste of like what's next in calculus. You will be graded on some simpler ones, but